Hello, my dear friends. In this class, we'll be discussing about vectors, integrations, and differentiation. This is very elementary class. If you already know this, still I would request that you please go through this class at least once. It may be that you learn something new. So, first of all, the course link is this. If you can enroll here. And the link is also given in the description of the video, whether it is posted in YouTube or Facebook, wherever you're watching from it. So the fees is just rupees 999. It is not 2000, which was originally planned, so it is given as a discount. So right now we go through the introduction. In the previous class we learned about dimensional analysis. And in this class, we'll be learning about vectors, not 2D polar coordinates, differentiation and integration. Everything will be uploaded in the course homepage. This is given in the description. The basic content what we'll learn in this class is vectors, its definition, its components, the definition of dot and cross product, differentiation, maxima and minima, the idea of velocity and acceleration, and integration, its definition and representation as area. So let's begin. What are vectors? A vector, any vector, you know, is a set of numbers which changes by following a certain rules when a coordinate system is changed. You get very much perplexed right now. What you have learned throughout now is a vector is something which have magnitude and direction both. Well, this is of course a property of a vector, but not a complete definition of a vector. Anything which have a magnitude and direction may not be a vector at all. So the actual definition of vector comes from the coordinate change, comes from how a set of numbers which is written as ax, ay, az in Cartesian coordinates. What are the numbers? Their coordinates. Their components, which changes by following certain rules when the coordinate system is changed. Well, we'll learn how the vector changes when coordinate system is changed. Don't worry about it. So when what are the main application of vectors? Vector actually reduces the number of equations to be written when expressing a law. Well, how? Say, if you write Newton's second law without vectors, you need to write three equations. Fx is max, or m dpx dt, or fy is may, or dpy dt, or fz is maz. That's very boring, I should have honestly. So, but if you write with vectors, the three equations can be coupled as one single equation. This f is ma. So that is one very useful use of vectors in physics. When you write vectors, vectors can be written as a bold font or a line over it. Like this notation, you know that, you already know. Both notations are used. So, and we'll write both notations. And sometimes you see a strange hat. This is nothing but an unit vector. A vector whose magnitude is just one unit. The modulus magnitude of main vector is written around this. I'm unable to select it correctly. So, okay, leave it. You're watching the magnitude of the vectors is written like this. So, okay. Next, we'll introduce some basic laws. You might not heard about those laws till now. Okay, see by one by one. One is the closure law. First is closure law. If A and B are two vectors, then A plus B is also a vector. You know that, okay, but you haven't thought about that this could be, well, an additional law. But yes, this is told as, this is defined as a closure law. If A and B are two vectors, then A plus B is also a vector. Just like if one human and another human, if you add both, they will be humans. Like this, if you have integer numbers, one integer is 5, another integer is 7. If you add them, 5 plus 7 is 12. This is another integer. So that is called a closure law. We'll discuss closure law in great details in another course, mathematical physics. Okay. Now next thing is commutative law, addition. Commutative law with respect to addition. A plus B equals to B plus A. If we add 5 plus 7 or 7 plus 5, it's the same. So in the same way, if you add two vectors, if you add B vector with A, this is same as if you add A vector with B. The third is called associative law. It is also with respect to addition. This is if we add in three vectors, the order of addition is not important. If you add B plus C first, then add with A, that is the same as if you add A plus B first and then add C with them. Next is associative law with respect to a scalar multiplication. The thing is, say the C and D, which are written as not as bold font, they are called scalars. They maybe write maybe an integer number, maybe a fractional number, say, or maybe a floating number like 3.758 or 53 by 72. These are scalars. So if you multiply C and a scalar number with the multiplication of D and A, so we multiply D and a scalar with A, then multiply C with it. That's the same as if you multiply C and D first, then multiply A with it. So that ordering of scalar multiplication is not important, just as the addition of vectors, the order of additions are not important. These are called associative laws. There will always be a null vector or zero vector. A null vector is what? A null vector is a vector which does not have any magnitude but can be called a vector, or in principle a vector, and that is also for mathematical, like to satisfy the mathematical addition, subtraction, or etc. You go through any your basic book of vector, class 11 and 12. So you get the examples of null vectors. Don't worry about it right now. Vectors can be negative. If A is a vector, there will always be another vector which is minus A, and A plus minus A will be 0. That means whenever you have a vector, there will be a negative vector. If you have A, you always have a minus A. If you add it, you'll get a null vector or the zero vector. Finally, the distributive law. If you are multiplying C and a scalar with A plus B, two vectors, we'll get C multiplied by A plus C multiplied by B. C multiplied by A plus B is CA plus CB. C plus D multiplied by A is CA plus DA. This is called distributive law. So what we have? Closure, A plus B are two vectors, then A plus B is also a vector. Commutative law, A plus B is B plus A. Associative law, A plus B plus C, B plus C added first is A plus B added first together with C, then added with C. Associative law, C multiplied with DA, C and D are scalar, is CD multiplied first and then multiplied with A. So associative law with respect to scalar multiplication. Then there is a null vector, A plus 0 is A, and if there is a vector A, there will always be a minus A. If add them together, we'll get a zero vector. Distributive law, C multiplied by Ci is a scalar. A plus B is Ca plus Cb. C plus D multiplied with A is Ca plus DA. So these are some very important properties. The significance of those properties you will be learning slowly. So now it's time to have a representation of vector addition. I guess you all know it. But say this is a geometrical representation. If you have your A vector like this, and if you start your B from the tip of A, your A plus B vector will be like this. This is just a triangle law. A plus B start from the beginning of A and ends at the end of vector B. Just as you see, if this is your B, this is your A, this is B plus A. As simple as that. If this is your A, this is your B, this is A plus B, and a parallel vector, the same vector actually. So if this same parallel with same magnitude, so this is B, this is also B, this is A, this is also A. So this vector A plus B is same as B plus A. So this is just a parallelogram law of vectors. Generally, the two parallel lines with same magnitude and same direction of arrow represents the same vectors. This is very obvious to you. Okay, now the basis vectors. So what are the basis vectors? Basis vectors are a set of orthogonal. Right now, the meaning of orthogonal to you should be the mutually perpendicular. So basis vectors set of mutually perpendicular unit vectors, one for each dimension, x, y, z. These are called dimensions. So one for each dimension. So we have three dimensions in Cartesian. The base vector lies along x, y, and z axis. So this is your x axis, this is your y axis, this is your z axis. So to visualize, I just drawn the parallel planes also, xy plane, this is xz plane, this is yz planes. The unit vectors are written in many formats, like I cap, j cap, and k cap. This is one type, one way to write it. Bold I, bold j, and bold k. This is another way to write it. Ex, ey, ez as bold. This is another way. E1, E2, E3, a general format. All means the same. The basic property of unit vectors are, if you, I will introduce the dot products also in more detail. But if you just have a dot with I dot I, is j dot j, is k dot k is 1, you all know it. And if you have a dot product with multiple, with different unit vectors, as they are perpendicular, so I dot j is k dot j dot k is k dot I is all 0. And if you if you have a cross product, I cross j will be k, j cross k will be I, k cross I will be j. They works like in they works in circular permutation. So if you have I here, j there, and k here, there you have a circular permutation. If you have I cross j, it will give you k. But j cross k, it will give you I. If you have k cross I, it will give you j. The whole thing is circular permutation. To reverse the direction, you will get a minus. Okay, guys. Now how we represent a vector? We generally represent either by an comma. Just if you can write a vector as just like this: 3, 5, -1. I change the color. Right. You can write a vector like this, or a vector like 3 hat I means 3I cap plus 5j cap minus k cap. I will understand the same thing. They means exactly the same thing. They mean we have components of vector 3, 5 and minus 1 in x, y and z direction. 3, 5, 1 etc. for the components of vector. Or the hills of the component. What do they signify? You may all know it, but still there is no issue by looking. So now before I go to the exact the component and all the detail, just let me define a scalar product or dot product. I define a scalar product or dot product between the two vectors a dot b should be ab cos theta. A and b are magnitudes of a and cos theta is the angle between them. So if you have a and b are two vectors, dot product means you will get magnitude of a, magnitude of b multiplied by cos theta. I need to draw a and b from one single point. So we can say it like this: a times the projection of b on a, or b times the projection of a on b. If we have a like this, and if you have b like this, so b cos theta, you can simply say a remains intact and b cos theta. So b cos theta by simple trigonometry comes like here. This part is b cos theta, and I can imagine like this is the projection of b on this vector. Have you heard about mechanical work done? The work done uses the concept of dot product. In terms of components, a dot b will be ax bx plus ay by plus az bz. I assume that you know what other components like. This 3, 5 and minus 1 are called the components. This is ax, this is ay, this is az. And this 3 is ax, 5 is ay, minus 1 is az. These are components. Okay. So in terms of component, a dot b is this multiply the x components of a and b plus multiply the y components of a and b plus multiplied by the z components of a and b. You can pause the video and take and try to answer. If you have a and b like this, what would be a plus b, a minus b, modulus of a, modulus of b, and what will be the a dot b and the cosine of angle between a and b. You just have a quick revision on that. If you forgot all of those, just do that. See the definition what I have written in the previous slides, and you try to answer it. I think everything will be clear. I believe you should get all those right. These are a and b. So a plus b is, so just add the component. Add component wise. Add 3 plus 2. Add 5 plus 7. Add 7 minus 1. A minus b, you just subtract those components. Modulus of a will be square root of 3 square, 5 square, 7 square. That means square root of the component square. B will be the same thing. A dot b will be the ax, bx, ay, by, az, bz. Cos ab will be a dot b by mod of a and mod of b. Very simple. If you forgot this, pause it and watch it. This is a very important concept which will be required every time in this course and everywhere in physics. Just 1 second. Okay, then what next? Vector product or cross product. I define the vector product as, see, the most important difference is your dot product, the result was a scalar. This was not a vector. But here you see C is a vector. I define A cross B. is another vector C, whose modulus of C will be AB sine theta. Theta is the angle between them, the smaller angle, and direction of C is the perpendicular direction of the plane of A and B. So if you have your A and B and have an angle theta between them, you can always imagine a plane which contains A and B. So let's say A and B lies in a plane. So if you have two vectors, you can always think a plane between them. Your C vector will be another perpendicular, another vector which lies perpendicular plane at perpendicular direction of A and B, and which will be perpendicular to A and B. And what else? Its direction will be A and B. If you have a screw circular, you make that screw rotate from A to B. The direction, here A cross B and B cross A are different. The order of cross product direction are important. So if you have, if you rotate that screw, it gets to the direction of C. This is called right hand thumb rule. The order of multiplication is very important there. So okay, have you heard about torque? In torque, we'll use this. What did I mean by smaller angle? Say, if you have A and B, I can say, well, you have another, say it is 30 degree. I say A and B have 270-degree angle between them. Technically, it's also right. That's why we see the scalar angle, sorry, the smaller angle. Okay, so no issues. Cross product represent as area. So A is base and height. So C cross D will be the area here. And the direction of area is the normal to the direction of plane. So if you have C and D lies in a plane, the area which covers C and D, actually the area vector, the area scalar is this area vector is the normal direction to the vector. So okay, so I think you got it. C cross D is CD sine theta, and CD sine theta is the area. This is the base, this is the height. Okay. I think you all know the basic trigonometry, so I don't. What is base, what is perpendicular, what is hypotenuse, what is sine theta, what is cos theta, what is tan theta, and some identities. If you want to see more trigonometrical identities, go there. Just see your plus 12 level of trigonometry books. But still, I thought that I should include a slide of trigonometry, at least the definitions. Okay, now I see the components. Okay. So if you have a vector A, you project your A on x-axis. So that projection OB becomes the component. That is the geometric definition of the components. The components are the projections on the x, y, and z axis. This AX is OB. If you project your vector on this y-axis, this OC, this is your AY, the component of A on y-axis. The modulus of A is AP, OP of course, and just basic trigonometry, you see that cos theta is OB by OP, OB is OP cos theta, so AX is A cos theta. The component OB is nothing but A cos theta. The component OC is nothing but OP sine theta. So here the component of AX will be A cos theta, AY is A sine theta. I'm not going to very great detail because I assume that you somehow have a rough idea all about on all those. So if I write a vector as a component, I write as an AX I cap plus AY j cap. And as you see, OP square, in a simple geometrical property, OP square is OB square plus PB square. It's called Pythagoras theorem. And modulus of A, which is OP, this should be OB square plus BB square square root. So modulus of A will be AX square plus AY square square root. The angle tan theta is PB by OB. It's a geometry. Just visualize in terms of simple geometry. Tan theta is PB by OB. It's nothing but AY by AX. So the whole this slide is actually a very basic geometry. So if you're not understanding the geometry, you're not understanding the trigonometry actually. The definition of cos theta, the OB, so that becomes your AX, that becomes your AY. The AX is the definition, OB, the definition of AX is the projection of vector on OX axis. So don't worry about it. So if you're not getting anything in this discussion, so please contact me. Please have a ping on the group if you're already enrolled the course. So just give me a ping on the WhatsApp group. So okay, we have another visualization in 3D. Say this is your x-axis. This is coming from the page towards your eye. So this is your x-axis. This is y-axis. This is the page. And this is the z-axis. So your I cap, j cap, and k cap in this direction. Cap there. So your vector A will be written as AXI plus AYJ plus AZK. And if you have a vector A, you can have its projection. First project on the XY plane. This is the projection. This is the first projection. I shouldn't like this. I will delete that. First project on here. Then project there. This is second projection. This. So I'll delete those. These are not. They don't have much meaning at all. But I'm trying to visualize. I'm trying to make it visualize to you. If you have any arbitrary vector, make it project on your XY plane first. Make it down in your XY plane, but not completely, with magnitude. So it's not a directly you down it. If you down it, this magnitude will be same as this magnitude, but that is not you want. You see just a straight line. You draw a straight line from the tip of the vector to the XY plane and add it from the origin. This will be your projection on XY plane. Then you project it on then you project it on your X axis, and then you project it on your Y axis. So this become your AX, this become your AY, and when you are making the projection, you make another projection on that. You make another projection on the Z axis. So that projection on Z axis become your AZ. So I delete those. They don't have much meaning at all. This arrows also does not have much meaning. So you need to do 3-4 projection. First projection here, then there, then there, then there. So all the AX, A1 and AZs are mathematically written as AX is A dot I cap, AY is A dot J cap, and AZ is A dot K cap. You just think about it, that why does AX become A dot I cap, and tell me what did you get it from here. Okay, so then we are spending very much time on the basic detail. Okay, now it's just to verify your A cross B. So if you have your A as written as component and B as written as those components, if you do a cross product of it, it will be like AX BX I cross I cap plus AX BY I cap cross J cap plus AX cross BZ. That means AX BZ I cap cross K cap. Here is an I, here is an K. So I cap cross K cap. plus this ay multiplied with all the three terms plus az multiplied with all the three terms. You just need to verify it, this thing, and if I write this as in terms of matrices, this determinant of this matrix I, j, k, ax, ay, az, bx, by, bz, this becomes this determinant of this. Of course, you know the definition of determinant. I, ax, by, ay, bz, sorry, ay, bx, and the rest of the two terms. You just verify this is same as this. Verify it. Okay, we are not yet, almost half. Pause the video here and just find the answer. If you got it right, it's very simple. You use that definition. You use this. Whenever you have three components written given, a cross b will be I, j, k, and you write the components in terms of, here in the first row you write a, the components of a, 1, 3, minus 1, and in the second you write 4, 1, 3, and just calculate the determinant. B, a cross b, again you pause the video and please find those. It's a very simple exercise. A dot bc, a b dot c, a cross b, all this, and yes, all the answers are there. So please find it. Simple exercise. Okay. Now derivative. Okay. We finish all this. Make a pause here. Then we'll tell you what is a derivative. Okay. The derivative is rate of change of a function. If you have a function, say this, increasing or decreasing, here it's increasing. So the derivative is if you have a value of your fx here, the function, and if you have a value ax here, your a increases. So that increment here, the function, I should draw you the red line to identify what the function is. The function is this. So this is increasing. Okay. So that how much the function increases? The function increases by delta y. In how much x it takes to increase it delta y. How much x was required? How much x is taken to increase this delta y? That is delta x. That means if you increase throughout x-axis by an amount of delta x, you increase your y-axis by delta y. Your function increases by delta y. So the definition of dy dx is limit delta y by delta x, and this limit tends to 0. We don't take that big amount of delta x, very simple small delta x. So please have a recap of your definition of derivative in whatever books you have, and if you don't have, it doesn't matter. So basic definition is this: f x plus delta x minus fx by delta x, limit delta x tends to 0. So then you calculate all the limits and calculate all the derivatives. I don't repeat all the process here, but I just repeat some of the basic derivatives. ddx of x to the power n is nx to the power n minus 1. You all know it, I guess. E to the power x is a to the power x. ddx of log ln ax is 1 by x. Think about it. Okay, ddx of sine x is a cos x, cos is this, is this. So all these are basic derivatives. You revise what the derivatives is. Derivative is basic by geometric definition increment, and more importantly, derivative will be tan theta. Now again look at a function. Here if you say a function is going like this, think about at the point P. Perhaps at the point P, so if you are increasing this x as x plus delta x, slight, it will be very small. So then your y increases by this. So if you make it very, very small, then your this increment and this increment will be the same. This angle here, the angles looks they're different. This angle and this angle are not exactly the same, but as you make it smaller, smaller and smaller, as you can imagine that your tan theta, at your delta y and delta x will be your tan theta itself. You can see, make it more smaller. So this, and then this is your delta x, this is your delta y. So this will be theta. So that tan theta will be as most as same angle as the function is increasing. So the gap between these two angles, between this angle, which is an ideal straight line, and the function, how the function changes, it increases as you make your delta x bigger and bigger. But as you make your delta x very smaller and smaller, that two thetas are very same. So derivative is the slope of the graph at that point. So dy dx at point P is tan theta at point P. It's the slope of the graph at this point. If you are not getting is anything, so first please ask me. Then I'll refer you something, and then you again come back here. Okay, you just calculate the derivatives. These are very simple. So then these are the answers. This is a very simple exercise of class 11, 12 mathematics. Okay. Then I would go to maxima and minima of a function. This is again, I assume that you have read it somewhere before. So if you have your function like this at point B, this function turns around. So I can say this is a minima, but I don't know whether it is a global minima. I mean, there could be another point where the function goes below B. So I'm not worried about it. I'm saying, okay, surrounding the point B, your B is the minimum. It's in the neighborhood of B, near about B, B is the lowest one. So this is that's why B is called the local minimum. Okay, so here at point Q, this function again turns around. So it's called a local maximum. And then near about in the neighborhood of Q, the Q is the highest point. And your X point cannot be said as minima or maxima. It's called a saddle point. It's called a saddle point. The implications of saddle point will become more clear as when we learn the two variable calculus. But saddle point is neither minima or maxima, or can be said at one side you can think about it as a minima, and in another side you can think about a maxima. Okay, we'll do it later. But it's a one-dimensional problem. The function here is a function of x only. So here we see at both minimum and maximum or saddle point, these all points are called stationary points. At the stationary points, the first derivative of a function should be 0. d of dx is 0. And if it's a minimum, it's a local minimum at point B, the second derivative of your function should be greater than 0. Make it great. So for a maximum, your double derivative is less than 0. For a minimum, your double derivative is greater than 0. For a saddle point or stationary point of inflection, your double derivative is also 0. If you have your double derivative 0, then it's a saddle point. And you should keep another point in your mind, that double derivative changes sign through the point. Like this, before the saddle point, if your double derivative were positive, and after the saddle point, double derivative will be negative. So these are important properties. You might not have heard about the saddle points, but okay, you need to know it. Okay guys, minimum maximum definitions of saddle point. Okay, you just check that whether you got it or not. Like, find the positions and nature of the stationary points of the function. This is a one-dimensional problem. 2x cubed minus 3x squared minus 36x plus 2. You take the derivative, first derivative, df dx, this is this. Then you make this as 0 after this first step. If you do first derivative, make this as 0, so you get x equals to 3 and x equals to minus 2. At these 2 points, your df dx will be 0. That means at these 2 points, you will have either maxima or minima. Then you check the sign of your double derivative. You get double derivative d square f dx square. For x equals to 3, your double derivative is 30. So this will be a minima. For x equals to minus 2, your double derivative is minus 30. Maximum, for a maximum, double derivative is less than 0. For a minimum, double derivative is greater than 0. So just change. So you keep in mind, this will be the maximum, this will be the minimum. As simple as that. Okay, now I will tell you the definition of velocity and acceleration. Okay. Velocity is the derivative of position. Derivative. Okay, how the position changes. Velocity is a vector. So how your position changes as a vector. Position is also a vector. In one dimensional you might not get it, but still. So your velocity is a derivative of your position. Acceleration is the derivative of your velocity. Sometimes I write the derivative as dot. So dv dt I can write as v dot. Or v I can write it as x dot. No issues about it. So believe me, position is a vector. So okay, v is a vector. All these are vectors. When we are writing in one dimension in the component form, we may not write it as a vector, but whenever you write it in 2 dimension or 3 dimension, we definitely write it as a vector. Okay, acceleration is the derivative of velocity. Okay guys, in 2 dimension, the position becomes a vector, a true vector, and we write position as x I cap plus y j cap. It's a 2D Cartesian. Now, if we have velocity, I'll take a derivative of it. So that will be ddt of x I cap plus y j cap, and it becomes dx dt I cap plus dy dt j cap. So I take the derivative of each component separately and define the velocity. Acceleration will be again another derivative. So it will have dvx dt I cap plus dvy dt j cap. And so simple d square dt square, double derivative of a position vector. Okay, and the same things becomes in the 3 dimension also. The similar things, x, y, z, dr dt is this, acceleration is this. Okay. I think everything should be very clear to you. Velocity, we have dx, vy, vz. This is dx dt, dy dt, dj dt. Acceleration, we have ax, ay, aj. Right. This is another component form. So I can write it like that. Like this, vx I cap, vy j cap, vj k cap. And I can write it as ax I cap, the component of acceleration, ay j cap. Okay. Say if you have a position vector is this as a function of time, tq plus 2t I cap. It should have been in hat, or if we write in a bold form, that is simple, okay with it. As a function of time, tq plus 2t I cap minus 3 to the power minus 2t j cap plus 2 sine 5t k cap. Now you need to find velocity dr dt, modulus of velocity, acceleration, modulus of acceleration at some point of time, any point, t equals to 0 or t equals to 1, or any point of time, you need to find it. Okay, so simple. Shikardan says that's very easy. You make a dr dt. What else? You take a derivative of all of this. ddt tq plus 2t, then ddt of minus 3 to the power minus 2t, ddt of 2 sine 5t, then you get all this 3t square plus 2 6e to the power minus 2t plus 10 cos 5t, and just put at t equals to 0, you get your dr dt. And at t equals to 0, if your dr dt is this, your modulus of dr dt is just 2 square plus 6 square plus 10 square. It's as simple as that. D square dt square will be simple as ddt of another derivative of this, but you keep in mind, when you are taking a derivative, don't take a derivative after you substitute the value of t equals to 0. You're understanding my words, right? You need to find acceleration at t equals to 0. You should start from the definition of your position or velocity, which was given as function of time. You don't start from here. Here this isn't constant. If you start from here, your acceleration will be 0, just 0. But don't do that. Your dr dt is this as a function of time. You take another derivative of this, then you substitute t equals to 0. So you make another derivative of this, you get this, then you substitute t equals to 0, and you get this. And after you get this, the mod of 12. These are some very elementary mathematics. You will need it any point of time. So, okay guys. Now a brief introduction about uniform circular motion. We'll do it later also. We'll do it vectorically here. If a particle is rotating like this in a plane circular motion, your O is the origin, R is the position vector. R is, don't worry about A right now, R is the position vector. Uniform means your angular velocity is constant. That means that your theta, the angle, is directly proportional with time, and that d theta dt is omega. This is for angular velocity, and the angular velocity is constant. Okay, so uniform circular motion at any point of time can be represented as a projection of R. You can see your x component is nothing but r cos omega t, this part, and your y component is nothing but sine omega t. So this is your r vector, and this is your theta angle. Okay, so your r is as a vector as r cos omega t I cap plus sine omega t j cap. If you're not getting how it's happening, think about geometry once again. If this is your r, this is your x, and x is r cos theta, y is r sine theta, and as it's an uniform circular motion, your theta is omega t in terms of your angular velocity. Omega is d theta dt. So then your r becomes this, and if your r becomes this, your modulus of r is constant. r square cos square omega t and r square sin square omega t, and whatever your t is, this cos square and sin square will give you always 1, so modulus of r will remain constant. That's an uniform circular motion, is like, if that circle means the radius of that circle will be always remains constant. And your velocity dr dt is r omega, take a derivative of it, it will give you minus sin omega t I cap plus cos omega t j cap. And if you imagine, you see that your v will be in this direction, just think about its direction. You can also verify it if you just take a dot product of your v with your r. See, this was r, so take a dot product of v with your r and check it that this will be always 0. You can see this is adding up, so you do it. And your acceleration, this is very important. If you take another derivative of it, you get your r back. Of course, 2 derivative of cos and 2 derivative over sine will give you cos and sine back. So you get acceleration as minus omega square r. So there is a minus there. So the direction of your acceleration will be towards center. Direction of your acceleration will be towards center, and with a minus omega square multiplied with your r vector. Okay, that's simple. Just starting from vector. In what I did is I wrote uniform circular motion as a vector. Just define your position vector of uniform circular motion is this, and if I define your r like this, all the results comes directly from it. All the centripetal acceleration, your tangent velocity is tangential component only, no radial velocity, each and everything comes if I just define r as this. And to define it, you just need to think about geometrically and define your r just like this. Okay, so that's about uniform circular motion. Integration as an area, you know, if you define an integration from a to b, your integrand is fx dx. This is actually the area which fx covered, the function covers, when it goes from a to b. The shaded area is the integration. Just a definition. A to b fx dx is this shaded area. Okay guys, if you divide this in small blocks, then your a to b fx dx is the sum over all the small blocks position, height, middle of that small block, and the small blocks width. That means what I am trying to say is there's this area, say, plus this area, plus this area, plus all these areas. It's the bigger area. You add up all those areas. This is the area, right? This is the middle of that, right? Those are the heights. Those are the heights. And you multiply those heights with those weights, and you get those areas, and add those areas up, you get that integration. Okay. Integration is also the inverse of the derivative. If you have your df dx, say this is the capital F, this is the small x. If you integrate it, fx, this small fx, you integrate this small fx, you get fb minus fa, capital F. Again, think about it. If you have a function capital F, you take its derivative, you get another function small f. If you make this small f integration a to b, it gets fb minus fa. This is capital D dx of f. So okay, so this is called a fundamental theorem of integral calculus. There is another property: if you make a to b fx dx is minus b to a fx dx. At any point of time, if you're not getting, please make a pause, visit it, rewind it, ask me. So don't worry about it. Derivative and integration as its inverse. Integration by parts, you know, fg dx is f integration g dx minus integration df du g dx, or like this if you are taking this derivative like this. I think you all know this. So I think I don't need to go to more detail about it, because I need to keep it very quickly, sum it up. So very few common integrations are like this. Just to I believe you know all those. If you don't know, make a pause and watch those, write it down, you know, copy, please revisit your class 2 level of any mathematics book. So okay, that's it. In the next class we'll be discussing the data and errors, so-called error analysis. We'll do a little bit more than what you have learned in class 11 and 12. Error calculation and error analysis is very important in physics. So next class will be of error analysis. So the course link is this. Please register your course, officially be part of this course. The subscription fee is just only rupees 999, not 2000. So okay, you can anytime contact me here, my email, my Facebook group page and YouTube channel. So thank you for your patience, and thank you for your revision of all the basic mathematics part. Okay.